The first part of section 9.4 should look pretty familiar to you. This is a topic from Algebra 1 that starts off as just graphing lines like you're familiar with. If you look at the far left example I have here, this is a pretty easy line to graph. You start by putting in the x-intercept and the y-intercept, both of which are 3 for this line, and then you connect the dots. Very similar to Algebra 1. Now, the next two examples, they both start with the same basic line because equals 3 is still going to be part of the solution, but then there's more points that also have to get shaded in as well. So, for example, with this one here, greater than 3, what this means is we're going to have to shade in all the points where x plus y, when you add up the coordinates, you get a total bigger than 3. And that's all of this stuff over here. So the solution set here is the blue line and all of the green shading that we put in there as well. You get a similar thing with the second one over here. The blue line is part of the solution because if x plus y equals 3, that is part of the solution for this inequality. But then you're also going to shade in everything where x plus y adds up to less than 3. And that's all this stuff over here. So the part of this topic that's the same as Algebra 1 is this stuff here. If you're doing a two-variable inequality, you start by drawing the boundary line, and then you have to figure out which side you're supposed to shade. And that's usually pretty simple by just picking one example point somewhere, plugging it in, and seeing if it works. And that'll tell you which side to shade. Now, there is one part of this that's a little bit trickier. And to understand this, I'm going to take that last example there, and I'm going to sort of pick it apart into some more details. So let me come down here and compare this inequality here with the one to the right of it. Now, they look almost identical, so I'm going to use nearly the same picture. But the difference is that this one here on the right, I should not be including the x plus y equals 3. In other words, I shouldn't be including the blue line. So, am I supposed to draw something like this? That doesn't look very readable. How am I supposed to tell where the shading that's been done there, where the shading has its edge? So, what we end up doing here is we kind of compromise. There has to be a boundary line so that you can see where the shading stops. But at the same time, there shouldn't be a boundary line because it's not part of the solution. So what we do is we draw a dotted boundary line. And even that might be familiar from Algebra 1. You might remember that with this type of inequality, what we call a strict inequality, you use a dotted line. Other than that, you pretty much treat this like the other sort of problem. You start by drawing the boundary line. Maybe the boundary line is dotted, or maybe it's normal. And then after you get the boundary line drawn, then you figure out which side to shade by picking some point somewhere and testing it. Usually, if I get to pick what point to use, I'll use 0, 0, because it's usually very easy to plug in. Like here, if you take 0 for x and 0 for y and add them up, you definitely get something less than 3. So the Math 90 topic, the intermediate algebra topic that we're going to be doing, is where we do multiple a full system, multiple inequalities all at once. So one key idea in this problem is that the solution to a system is the points that work in all of the inequalities. So you have to be careful to only shade the parts that solve all of the inequalities, not just one or two. So be sure to do that right. Be sure to shade only the points that solve all inequalities. And I'll show you why that can get a little confusing in a second. So to begin this sort of problem, what you do in the start is you just treat each of these inequalities as if it was the problems we were doing a second ago. You just figure out what their boundary line is, figure out which side to shade. So I'll do them in different colors, so it's pretty easy to keep track of which one is which. This one I'll do in purple, and we just did this one a second ago. We know that it has an x-intercept of 3. We know that it has a y-intercept of 3. And if you look at the type of inequality it's got, we know that it's got a dotted line for the boundary. And then, to figure out which side we're supposed to shade, we plug in some test point, and 0, 0 is a pretty good test point to use. And if I put in 0 for x and 0 for y, that does work. You get 0, which we know that is less than 3. Now here's where you have to stop for a second. If I were to go through here and shade all of this, there's a good chance that a lot of that doesn't solve the other inequalities. So it's a little too early to be shading in everything that's on that side of the line. So I write myself a little note. I put little tiny arrows pointing in this direction from the line just to remind myself for later that this line, the included stuff, is the stuff that's down and to the left. Now for this next one, let's see. Let's use blue for this one. It's a little trickier to graph this one. So if you're looking at a trickier problem, you might try just making a table of values. If I plug in 0 for x, y comes out to be 4. If I plug in 0 for y, x comes out to be negative 2. So that's that point and that point. I'm going to connect those dots with a line, and notice with this type of inequality, equals is included. So I'm going to use a solid normal line, not a dotted line for this one. Now, which side of this line would we shade? Again, test some point, and again, I'm going to use 0, 0 because it's easy. If I plug in 0 for x and 0 for y in this inequality, I get, well, everything on this side comes out to be 0. Is 0 bigger than or equal to negative 4? Yeah, it's bigger than a negative for sure. So that side of the line is the side I'm supposed to shade. And again, I can't shade all of that because a lot of that stuff, like this stuff up here, that's on the wrong side of the purple line. So I just write myself a little note for later that from the blue line, I go down and to the right. And then I've got one more inequality to graph here, this one. Remember that if you have y equals a number, that's a horizontal line. And in this case, because of the type of inequality it is, it's also going to be a horizontal dotted line, down at negative 5. 1, 2, 3, 4, 5. So down here, I draw a dotted line horizontally there. And with vertical and horizontal boundary lines, things are a little easier than normal because trying to figure out which side you're supposed to shade for something like that is a lot easier than plugging in a point. Here, we just want to know where are the y coordinates bigger than, oh well, it's going to be up. You don't even need to know what it's bigger than. It's just the bigger y values, they're up. So just a little bit of common sense there, and you can figure out which side to shade for that one. Similar idea with vertical boundary lines. You just have to figure out which side the x's are bigger or smaller. And that's usually pretty obvious. So after you get all the boundaries drawn, and for each boundary you've got a little arrow pointing in the direction which you're supposed to shade from that one, you should be able to consider all those different directions and find the region that's inside of the purple region and the blue region and also the green region. And in this case, it happens to be the central triangle here in the middle. All of this stuff is down and to the left from the purple line, down and to the right from the blue line, and above the green line. Notice that by doing 3 boundaries here, I ended up with sort of a triangular region. That's not always the case. I could have had any region here, like for example, it could have been this stuff over here perhaps, based on the way the inequalities go. The other thing that you should be prepared for and consider as a possibility is, what if there were 4 boundary lines instead of 3 boundary lines? Or, for that matter, what if there's more than 4 boundary lines? That is a possibility, but really when people are writing up tests, once you've tested a student's ability to handle 3 or maybe 4 boundary lines, after that you're just kind of getting silly. So I wouldn't worry about sitting down to take the next test and suddenly being presented with something that has 8 different boundary lines and it takes you half an hour to draw it. That's just not a reasonable thing to worry about.